Hi, I'm Brian.
I'm Michael.
I'm David.
I'm John.
I'm Nora.
And we're Team 12, and today we're going to be presenting our midterm project, Concrete Column.
The following are the position titles and working hour factors of each individual team member. John Lee is the design lead, Michael Peterson, the construction lead, Nora Quillman, the analyst, David Tran, the modeling lead, and Brian Wong, the project manager.
The column is 15 inches high and has a diameter of 1.5 inches. It has a hydrostone base that is 5 by 5 by around 2 inches. The column is made of plaster of Paris and has steel wire reinforcements in both the longitudinal and transverse direction. There are 14 vertical wires distributed evenly around the diameter of the column and a spiral of thinner wires acting as transverse reinforcement.
Testing apparatus. The column is actually clamped down to the table at the hydrostone base. These two threaded rods were attached to the linear actuator, and the actuator would pull the column back half an inch and then push it forward half an inch, recording the force for each displacement. And then after half an inch it would pull it back an inch and then push it forward a full inch. And the cycle would be repeated until 1.5 inches.
SolidWorks was used to draw a scaled model of the column. Because it was only for visual aid and not for analysis, certain shortcuts were used. The transverse steel was modeled as hoops rather than a spiral. The default materials for concrete and steel were used for the column, and half of the column was left bare to show the transverse steel and longitudinal steel that reinforced the column.
As for the total cost of the column, $10,000 was used for the column itself, the plaster of Paris, $13,000 for the hydrostone that goes into the foundation, $500 for the transverse reinforcement, and then another $4,000 for the rebar that goes into the column, for a total of $28,000 for the column.
As the testing results show, the raw displacement of the column was 3.878 inches. The maximum force was 14.526 pounds, minimum force was 2.705 pounds, and the average of which is 8.6155 pounds, which is lower than the 10-pound necessary requirement for competition.
For the predicted results, we thought it would crack at around 0.3 inches with a force of 30 or so pounds. However, in actual testing, the beam cracked at around maybe 40 pounds, but it only had an average of 8 pounds force. To account for the discrepancies between the predicted and the actual testing results, we came up, we thought it would be the actual plaster of Paris mixture ratio. When we first poured, this bottom portion here is actually 2:1 plaster of Paris to water. However, trying to pour the whole column was problematic and resulted in it not flowing as we thought it would be. To make it more liquidy, we added more water, making a larger ratio of plaster of Paris to water.
During the test, we found that the plastic hinge actually formed at the juncture of where the 2:1 ratio and the 1:1 ratio plaster of Paris met, and it was much higher than where it should have normally been. Additionally, the wetness, the 1:1 ratio for plaster of Paris to water made the plaster of Paris wet during the testing. It wasn't able to dry in time, and inside the rebars and the transverse reinforcement was rusting, so it was much weaker than it should have been.
Our column was a bold design. Our modeling in AlphaCalc showed through the moment curvature analysis and PM diagram that the column would satisfy design criteria. However, construction difficulties proved to be a significant challenge. When pouring the plaster of Paris, the mixed ratios led to a segmented column as well as a column that was too wet come test day. This has been Team 12's presentation. I hope you enjoyed it. Have a good evening.